Welcome back to part 3 on barycentric coordinates. First, I want to take a little detour and talk about the coordinates we've been using. And not just the whole topic, but sort of the idea that when we have a point x, y, z, that x plus y plus z has to equal 1. Well, sometimes some of the points that we find in our geometry problems, if we have to sort of impose the sum being 1, then their forms can get a little more messier than they should. And what I'm getting at is sort of take the equation of a line. So we have ux plus vy plus wz equals 0. And we know that x plus y plus z equals 1. But if we were to multiply the entirety of this equation by some constant k, then what we get is that u times kx plus v times ky plus w times kz is equal to 0, obviously. And we also have that kx plus ky plus kz is equal to k. So if we scale up each of our coordinates by some number, then specifically, if we go from the coordinates x, y, z, and we scale up, and we look at the coordinates kx and ky and kz, then if we plug these coordinates into a line, then we still get 0 if these coordinates were on the line. My point is that this equation is what we call homogeneous of degree 1, which means that each term is some amount of constants times a variable or multiple variables, but the sum of the powers of those variables are all equal 1 for each term. So here we have u, which is a constant, times x to the first power. So this is a first degree term. We have y to the first power and z to the first power. And then we have 0. If we can rearrange it so that each term is the same degree, and then we have that equal to 0, then this is a homogeneous equation. If we had anything other than 0, if we had 1, then it would not be homogeneous. Like this equation is not homogeneous because when we multiply, basically the idea is that when we scale up each variable, the equation remains unaffected. So since we scaled up each x, y, and z by k, here we don't get 1, we get k. So this isn't homogeneous, but this is, because when we scale up each thing by k, we still get it equal to 0. And it turns out that quite a few equations in barycentric coordinates have these nice homogeneous forms, including the form of a circle, and we'll see a theorem on the orthogonality of two lines that is also homogeneous, and just those things I can think of the top of my head. So if we have sort of x, y, and z, which have the same messy denominator but some nice numerators, then we can scale up and still be able to apply these coordinates to some of the equations we want to use and manipulate. So from here on out, we'll see a lot of points, and instead of commas, we'll put colons. And this will be used to denote that these coordinates are not homogenized. That this is representing the coordinates x divided by x plus y plus z, comma, and then, similar forms. Because if we were to add up each of these fractions, we would get on the top x plus y plus z, and on the bottom we have x plus y plus z, so the sum of these coordinates would equal 1. But we scale everything up by this denominator, this common denominator, so that we have easier forms to work with. So for example, the point 1, colon 2, colon 0 corresponds to the point 1/3, comma 2/3, comma 0. Now let's look at some special points that we often see in Olympiad geometry problems. We have the centroid, the end-center, the median point, the x-center, the orthocenter, and the circumcenter. Now, most people should be familiar with these 4 points. Now, if you're not familiar with the other ones, that's fine, especially not this median point. I didn't know what it was when I first even looked at barycentric coordinates. So it's fine if you don't know these points, but I will explain them as I use them. So all of these have very messy forms, and we see that orthocenter and circumcenter, these are 2 of the most used points, especially the circumcenter. We use circles so much in geometry that we would like a nice form to represent the center of a circle containing our triangle. However, we see that these points contain trigonometry in them. The tangent of A, tangent of B, tangent of C, and sine of 2A. We have to use double angle formulas. Well, there are algebraic forms of these points, but they are particularly messy, including like just squared things and, but later on we will develop some notation that will better deal with these problems, or better deal with these 2 points. So just, don't be scared of these, because we'll rarely use tangent A, tangent B, tangent C. These are just sort of little placeholders for other definitions of the points that we will often use. Now I should also, I guess I should have written some common letters we use to denote these points. The centroid is often a G. The end-center is an I. Some median point is a K. Now the end-center, I forgot to put etc. here. There are 3 x-centers for each triangle. Now the x-center is defined as, the end-center is, 1. It's the it's the intersection of each angle bisector of triangle ABC, but it is also the center of a circle that is tangent to ABC at its 3 sides. Similarly, the x-center per a specific point is the center of a circle that is tangent to one side and the extensions of 2 other sides. It is also the intersection of one of the angle bisectors and 2 external angle bisectors. So we have, like, if this were angle B, then this is the external angle to B, and so this line bisects that angle. So that's, we would denote that as IA, is the AX center. So there's the AX center, the BX center would be somewhere out here, and the C and X center would be somewhere out here. And so whatever letter we're using, we have, it's basically just the incenter, but with a negative. So the orthocenter, we usually use an H, my bad. And the circumcenter is often not a C, an O. So each of these points, we see that we're using the unhomogenized form. Now the only one with particularly nice homogenized form is the centroid. We see that the centroid is 1, 1, 1, which corresponds to the unhomogenized, or sorry, the homogenized point 1/3, 1/3, 1/3. Now the centroid is the intersection of each triangle's medians, which is, a line from one vertex to the midpoint of another. And we saw that the midpoints had nice 1/2, 1/2, 0 form. So it makes sense that we would have sort of an average here. And so yes, we can use sort of the ratios, because if you draw a line, or if you draw each median, then you're bisecting each side. And we saw that we can use the ratios of sides to define our points. So we would have, we can also use triangle areas, because if you draw in the medians, then you create 3 equal triangle areas, and that's pretty easy to prove. Next, the incenter has the form A:, B:, C. And this is just using the angle bisector theorem, and it also uses the ratio of lengths. So the angle bisector theorem states that if you have a triangle and its angle bisector that hits here, the ratio of these two sides is equal to the ratio of these two sides. And so that would just be like B and C. And so we can use our 3 ratios, because that's true for each angle bisector, and the incenter is the intersection of each angle bisector. So we have 3 symmetric ratios, and so we can put those together into a point. Next is the symmedian point, which, again, like I said, is something I didn't even know when I started learning about barycentric coordinates. The symmedian, or asymmedian, is defined as the reflection of a median over an angle bisector. So it has a pretty weird definition, but it also has very straightforward definition. It's just a squared colon b squared colon c squared. And we can similarly get the form of any isogonal conjugate. An isogonal conjugate is the reflection of a point over the incenter. So in fact, the symmedian point, since we're reflecting each median over an angle bisector, is the reflection of the centroid, which is the intersection of the medians, over the incenter, which is the intersection of the angle bisectors. So if we reflect G over I, we get K, and it has a squared, b squared, c squared coordinates. Next is the AX center, which I know this looks like a B after I drew this line, but similarly, since we know that we can use we can use the angle bisector theorem to prove this, but we can also show this using the incenter excenter lemma, which actually no, sorry, no. We can use the area definition, because we know that the excenter is the center of a circle that's tangent to these 3 sides. And whenever we have tangent circles, we like drawing perpendicular radii. And so, since those radii are all equal, we have basically 3 equal triangle areas, and we can get the definition of this point. You can do a similar thing with the incenter, because if you have an incenter and you drop its radius, which is usually denoted with a lowercase r, then this area is just 1/2 AR. And similarly, you would have 1/2 BR and 1/2 CR, so you would just have A, B, and C. So for the excenter, since it's outside of the triangle, specifically it's outside facing A, then you would still have or not three equal, but um, three areas that are in these proportions. But since this one, the IABC is you're going clockwise, so you would have a negative area there. Then the orthocenter and the circumcenter, you sort of just chase around some angles and use the area definition to get these forms. And then you can use law of cosines and sines to get the algebraic forms. So I'm not going to go over any proofs of these points, although in the future I might do a video about the Samedian point and how we get its coordinates, because I like sharing things that I learn. I find all of these 5 to be pretty easy examples, so I encourage you to do them for practice, but I might make a video about this one, perhaps not as a part of this series, but just on Samedians in general, because I hear they're useful in Olympiad geometry, but I don't know much about them. So that's it for this video. So we learned about unhomogenized coordinates, which we use a lot, especially because these expressions get messy. And we learned these special points. So there's more special points that also have known formulas and such, but they're not included in this list because they're used less often. Anyway, thank you for watching. I'll see you in the next part.